Hello. Good afternoon, everyone. I'm not sure it's afternoon, at least here it's afternoon, maybe evening, maybe morning, I don't know. So it's a great pleasure to receive the second speaker of today. It's Professor Fabricio Simeoni de Sousa from the Department of Applied Mathematics and Statistics at the Institute of Mathematical and Computer Science of the University of São Paulo, USP. He's a great friend of mine, for sure he is, and I consider him one of the most distinguished researchers in numerical analysis here in Brazil. And Professor Fabricio holds a degree in mathematics from Neste, and the master and the doctorate in computer science and computational mathematics from USP. And he completed postdoctoral research at Delft University and also University of Texas at Dallas. Currently, he's an associate professor in the Department of Applied Mathematics and Statistics at ICMC USP. He's also one of the coordinators of the Center for Mathematical Science and Applied to the Industry, CPID-CMI, here in Brazil. He's the coordinator of the Laboratory of Applied Mathematics and Scientific Computing, among other relevant positions, includes the coordination of projects in collaboration with Petrobras, the Brazilian oil company. He's editor-in-chief of the journal Trends in Computation and Applied Mathematics, has experience in the area of applied mathematics with emphasis in numerical analysis, mainly working of the numerical solution of differential partial equations via finite difference, finite volumes, and finite element methods. And today he will discuss part of his research here with us. And we would like to thank him again for this excellent opportunity to learn a little bit more about the numerical simulation of fluid flows. So Fabricio, thank you very much for joining our seminars here, and the stage is yours.
All right. Well, thank you very much for having me. Thank the organizers and especially to Michael for this kind introduction. Thank you very much. A little bit exaggerated, but that's all right. Yeah, thank you. Well, I'm going to talk today about this project that has been for quite some time already. The multiscale method, domain decomposition methods, and now the efforts that we are employing to build preconditioners based on these multiscale domain decomposition methods. So I want to just show here all the collaborations that we have. These results that I'm going to show here is an effort from all these people here. Especially Professor Gustavo Buscaglia, who sadly passed away this year, and all these postdocs actually all of them are former postdocs right now, in the bottom row, and also the funding from Petrobras, FAPESP, and CNPq. Let me give you some motivation for this work. Petrobras has approached us quite some time ago, asking for us to develop new methods that could scale well in this high performance environments, like this supercomputers and etc. By that time, there were little development in this area. So we started to take a look at these multiscale methods that are basically domain decomposition methods. I'm going to talk a little bit about that. But the main objective here is to aim towards some scalable simulations with a very high number of unknowns, right? And the main application is the simulation of fluid flow in petroleum reservoirs, like the ones that we have in the pre-salt area here in Brazil, right? But first, let's talk about this model problem. Actually, we are considered here this a single phase Darcy flow. Actually, is an elliptic PDE, right? With this kappa here is a heterogeneous coefficient that might be the permeability field for this flow, right? And the main idea of this domain decomposition methods is to break the domain, the main domain in several subdomains, and such that we can solve smaller problems in each subdomain, problems that don't talk to each other, so we can solve that in parallel, for instance. And then, of course, all the solutions are not the solution of the overall problem, but then we can try to glue these solutions together by imposing some condition. For instance, for this kind of problem, the Darcy flow, we can impose the continuity of the normal fluxes and continuity of pressure at the interfaces between subdomains. So that's the main idea. The multi-scale comes when we have actually like very different scales. The small scale that is reserved to the details of the flow, that is this smaller grid here with a small h, and a larger scale that is the size of the subdomains. This is capital H here. And the idea of the multi-scale methods is to impose, is to weaken a little bit this compatibility condition, imposing them on the larger scale instead of the smaller scale, so that we can arrive with a method that can have good performance and solve this problem much faster than the original one. There are many ways to do that. Each way will lead to different methods. So I'm going to discuss here the method that we have been working and developing in the past few years. So this is the multi-scale Robin-coupled method. So the idea is, like I told you before, is to solve these local problems here for the blue unknowns. That this is a mixed formulation, so we have to solve for fluxes and pressure on this blue grid here, and then the coupling between subdomains will come from the Robin boundary condition that is imposed on the interfaces that are the red ones, and this is done by using two Lagrange multipliers, one for normal flux and one for pressure, that they live on the interfaces. And the compatibility conditions are the weak version of those that I showed previously, that are these two equations here, that they impose continuity between subdomains. So ideally, we have to solve this problem here. It's a coupled problem. We have to solve that. Of course, this has much more unknowns than the original problem, so it's not feasible to solve it coupled like this. But we can take some advantage of the finite element formulation and write the solution that we are seeking as a combination of a homogeneous part and a heterogeneous part. And the homogeneous part we can write as a combination of multiscale basis functions, that the multiscale basis functions are basically the solution of these problems here. With known spaces for UH and PH, these red ones here. Of course, we have to discretize these Lagrange multipliers over the interface spaces, so we write a basis for that as a known basis with this phi j and psi j, right? And then we plug these bases here and solve each problem, and each problem will give rise to one of these phi that are the multiscale basis functions. And the last multiscale basis functions is solved to take into account the fluxes and the boundary conditions. So if we do that, we can take this formulation as it is, right? and plug in these two continuity equations here, right? So we arrive at an interface problem just for the unknowns U, J, and Pj. So with all that, we can build an algorithm. The algorithm is like this. The multiscale basis functions are computed in parallel, right? Because we don't need to communicate between subdomains to build that. So this is in parallel and without any, and we don't have to update it. For instance, if this is computed inside an iterative procedure, we don't have to update these basis functions. This is computed as a preprocessor before the solution of the problem. And the plus the heterogeneous parts to take into account the source term and boundary conditions. But all these parts here are local operations that can be done in parallel. The only global thing that we have to do is to solve this interface problem that comes from these two compatibility conditions. And the size of this problem is much smaller than the original problem. So it's like a model reduction, if you want. And once we have the solution of this interface problem, we will have these coefficients and we can build the overall solution using this combination of the multiscale basis functions. So with that, we can hope to achieve performance out of this method. So I will just show quickly here some of the previous results that we did. It's based on a Robin boundary condition, so we can take this Robin coefficient and make it very big, or very large, or very small. And by doing that, we approach asymptotically the solutions of well-known methods. One is the MHM method, and another one is the MMM-FEM method. And we can check that our formulation approaches the solution of these two methods in either when we increase or decrease the size of this Robin parameter. And what we found also is that in most heterogeneous problems, the optimal way that gives smaller error usually is some choice between these two external. So it's very good to have this possibility to impose Robin boundary conditions for this domain decomposition method. And this is another typical result that was applied for two-phase flows, and with some tweaking of the method and also improvements that we have published. And we see that this top right solution here is much similar to the fine grid solution, which means that our approach gives better results than the other that we compared to. And over here, for instance, we can see that the errors are about one order of magnitude smaller than the other traditional methods. And then with that we tested the scalability of this method, how it will perform when we want to compute large problems, large flow problems modeled by this Darcy flow. Over here, we can see what we call this, it's strong and weak scalability. The strong scaling on the left of this graph here on the left, what we see here is the number of processors and computational time. So we start with a number of processors here, so like 150. This is a problem. Almost 1 billion unknowns, right? This is a lot of unknowns. And we start doubling the number of processors, and we get a curve here in the computational time that is almost it's very speed up if we want the time to. And another type of scaling we of processor is the size of the problem, and time to solve that should be constant. So the ideal speed up is this constant curve here. I don't know if you can see it, but it's a constant time. And we see here that when comparing to another state-of-the-art method, that is the algebraic multigrid with the method, is a very good problem. We see that our method here, that is in green, scales very well when we increase the size of the problem up to 1.3 billion cells, as compared to the problem that lose a lot of here, million cells, and then it behaves more or less the same up to 1.3 billion cells. So this is a nice result of the method, but there is a catch. Since the conditions, the compatibility conditions between subdomains, what we get is a discontinuous solution across subdomains. Discontinuous on the smaller scale. Over here you see like 4 subdomains, and we see here a zoom that can show that over the interface we have discontinuous the pressure conservation on the large scale, but not on the small scale. We can overcome that by doing some post-processing or whatever, but it's additional effort to try to recover the solution. There is another way. That's what we actually are doing right now, is to try to convert this method in terms of a preconditioner. So what is a preconditioner? Just remind you what is a preconditioner. All these discretizations like finite difference, finite volume, or finite element will result in a linear system that you have to solve finally. And this can be solved. If you have large systems, you cannot hope to solve that with direct methods. We have to go for iterative methods, and for instance, conjugate gradient, GMRS, or all these methods. And these methods have slow convergence in terms of the number of iterations. So we want to improve the convergence by using a matrix that is a preconditioner. The precondition is actually a matrix that's an approximation of the inverse of the original matrix. We can do like left preconditioner, like a right preconditioner. Oh, it's I guess is wrong here. Actually, the one is the top one is left preconditioner, and the bottom one is a right preconditioner. And by doing that, we hope that the new system, we modify the original system, but the new system has to have the same solution of the previous one, exactly the same solution. But since we are pre or post multiply by this approximation of the inverse, we hope that this new matrix has a smaller spectral ratio, so the convergence of the predictive methods is faster. So that's what we are going for. So the idea is to build a preconditioner based on the MRCM. We will then, by doing that, produce the solution of the undecomposed case, right? Because the solution will be the solution of the linear system. That's the same of the original problem. But now it should be much faster, taking advantage of the scalability of the multiscale building of this preconditioner, right? So we will assume that we have a single phase Darcy problem solving for pressure. Yeah, we want to solve for pressure. The discretization will come from the standard finite volume method, the 2-point flux approximation. That's very standard in the literature. And we will use preconditioned conjugate gradient method to solve that system. So to start building the preconditioner, we have to recall the coupled formulation that I showed you before. Right now, I'm showing you the weak formulation of the variation formulation of the problem, the original problem. This is the same problem that I showed you before, right? The same, but now written in terms of variation formulation. And the two first equations here are the first one are the Darcy equation, the Darcy velocity, and the second one is conservation of mass, and the third and fourth are the compatibility conditions. If we start from this variation formulation and discretize it in terms of finite elements, and we arrive at this discrete system here. And now we transform that variational system. This discrete system is a coupled system, right? With all these block matrices here are defined by this inner products that we can specify in terms of the spaces that come from the discrete version of the variation formulation. And then by doing that, we can start now operating this matrix and try to isolate pressure from the other unknowns. We can do some tedious calculations, and we will arrive at this matrix here that we call MRCM. That is this matrix here, where this M here is this one here. It's built completely from all these blocks that I showed you before. And this is the preconditioner that approximate the original problem. So we did that in terms of this algebraic calculations. This is the algebraic formulation of the MRCM, so that we can have a matrix that we can prove that is symmetric positive defined. So we can use that as a preconditioner in the conjugate gradient method without any problem. Also, we can also compose this matrix with some pre and post smoothing steps. I will show you that this is our important steps in order to improve the solution that comes out of the method, right? But if you do that in this manner here, the matrix is still symmetric positive defined. So with that in hand, we can plug on the conjugate gradient method and start solving. The problem is that to build that matrix is a cumbersome computation. Actually, it's much more expensive than solving directly the problem. So, but what we do here, we don't compute this matrix actually. The way that it is done before, it helps us to understand and prove that this can be used as preconditioner. But now the assemble of the matrix has to be done in different ways. So what we do is something similar to what we have done for the direct method, right? But now we are doing that inside the looping of this conjugate gradient iterative method, right? So, and you might ask, well, you are trying to solve a problem, AX equal to B, and down here we have like this problem here. That is another problem that you have to solve with M. That it's expensive also. But what we do here is it's a high performance implementation of that. Actually, we take advantage of the multiscale basis functions that can be all computed outside this iterative process, so that the only cost that you have here for each iteration of the conjugate gradient method of the global reduced problem of on the interfaces, that is this line here, right? So this is becomes very cost effective as compared to the solution of the original problem, as I will show you the results. So that's what we did. So I will show you some results of this method. Over here, we did some calibration actually, because we have many things to choose on. The domain decomposition itself it's arbitrary because it's not a physical thing. We want to do that in order to solve the problem in parallel, right? So we can do that arbitrarily. And also we have the calibration of the Robin parameter that we did. Then we have to choose which Robin parameter is best for this case. Actually, we found out that this smaller Robin parameters are better, right, for a better conservation of pressures. Richer interface spaces are preferable also because they give you more accurate solutions at the end. The size of the composition had no impact on the number of iterations, so we can choose that arbitrarily. And we had to apply some smoothing, which means that we have to use another method to try to smooth the solution a little bit. It's like a pre and post smoother before and after applying the preconditioner. This is important because of the discontinuities of the interface that the method has on the interfaces. But since this is inside the iterative conjugate gradient method, and also is done on the residuals, this has no impact on the final solution, only on the velocity that you achieve, the number of iterations that you do, and etc. But we found out that just a small amount of smoothers, the smoothing steps are necessary. Just 10 or 25 is a sweet spot. I will show you some results. Well, this is a comparison. What we see here is the number. Sorry. What we see here is the number of iterations, right? And over here the relative residual. So we see that if we do not do any preconditioning on the conjugate gradient method, this is the red curve here, the method is very slow to reduce residuals. But once we apply our method as a preconditioner, we see that we can have, in the best case scenario here, 40 iterations to converge for this small problem here. But this is still not very good. We did further testing with a little bit larger problem, and we did also a part of all these calibrations that I showed you before, and compared with the algebraic multigrid method, and we see that we can achieve the same reduction of iterations as the algebraic multigrid, which is very good. We can reduce up to 10 iterations for this larger problem, a little bit larger than the previous one. So it means that our method can be used as a preconditioner with good results as compared to algebraic multigrid. But the problem is that to achieve that level of reduction of iterations, we have to use linear interface spaces, more richer interface spaces at the interfaces for the Lagrange multipliers, and which makes the interface problems larger, so the method becomes slower. And as a comparison here, like you can see that the best version takes only 9 iterations to converge, but takes like 60 seconds. And the first one, or actually the second one, that's the best option that we have here, is with weak coarser spaces for the interfaces, right? So the reduction of iterations is not so great, but the reduction in time is much better than the other case. So with this, this is what we found out with our calculations. Over here, we can see a bit of profiling. In colors here, you see the time taken for each part of the code. So let's focus on the blue curve here and the red curve here, just the continuous curve here. And we see the red one is the time to compute the multiscale basis functions, which I told you is parallel and done outside the looping. And the red one is to compute the interface problem. And we see, and over here, the x-axis here is the number of subdomains. So if we increase the subdomains, we can increase the number of processors, for instance, right? But then the size of the interface problem becomes larger, and the time to solve becomes larger and larger. So there is a sweet spot here. The black curve is the total time. Yeah, we for small number of subdomains, we have a reduction in time. But if we keep reducing the number of subdomains, increasing the number of subdomains, reducing the size of the subdomains, the time to solve the interface problem becomes larger and larger. So we have to choose some number of subdomains around for this spot in position. And this is a test to show you that the smoothing part is not doesn't affect the overall time. We see that here is the number of iterations, and over here the CPU time. On the x-axis here is the number of smoothing steps that we have to do. And you see that only with 10, 20 steps, it's enough to bring the CPU time down, right? But if you keep increasing the number of smoothing steps, nothing happens to the problem. We just take a little bit more time, but doesn't impact too much the overall time. In this case, in the right-hand side is another case that we see that we have a little bit of impact if we keep increasing the number of smoothings. So this is to show you that we have chosen like something around 20 smoothing iterations. It's enough to give good results for this problem. And finally, we can see the weak scaling of the method that we developed here. And we see here that on the left graph here, we see it's a smaller problem. You see that we start with 14 million unknowns and increase up to 120 million unknowns. And it's that story. We increase the number of unknowns and also increase the number of cores, and we hope that these curves should be constant. And in black here we can see the algebraic multigrids. We want to beat them. I mean, we want to compare to this algebraic multigrid. And in red and blue are versions of our method. And we see that over here we don't see much. But then when we increase the size of the problems up to a 250 million cells, we see that our method starts getting very good scalability. Remember that this should be constant as compared to the algebraic multigrid, which is very good in terms of scalability of this preconditioner, right? There is another catch. Actually, we found that if we increase too much the contrast is the ratio between the largest permeability and smaller permeability that you have on your porous media, right? And the realistic ratio, realistic contrast that we have is around 10 to the 10. So we are around here. And we see that if we go to this realistic permeability field, which is a lot, our gain is just a little bit over the algebraic multigrid. Algebraic multigrid doesn't, over here you can see that if we increase the contrast, our method starts behaving not as well as we want it to be, right? And the algebraic multigrid doesn't change too much. So our method still suffers from this ratio of this contrast, of this ratio of permeabilities. But I mean, in some cases like 10 to the 7, 10 to the 8, we can have a good improvement over almost twice as much faster than the algebraic multigrid. And this test here is another test with a very harsh permeability field that you can see here in these views in blue. And we also did a bit of profiling, evaluating what each part of the method is taking, how long each part of the method is taking. But what we wanted to that you take a look here is that we increase these problems here up to 500 million cells, and we see that the weak scaling is very good as compared with the algebraic multigrid that you see here. Ours keep a constant CPU time. If we increase up to 125 processors, and the algebraic multigrid increases much more than that. And this is another example of the same problem, also with almost 500 million cells, and compared with algebraic multigrid and with also these preconditioners that has just been published on the literature from Ye and Chung, and we see that our method behave very similar to them, right? And better than the algebraic multigrid, the both methods. Well, so this brings us to the conclusion. We have successfully developed this preconditioner based on this multiscale domain decomposition methods, and we have showed that we can, by doing that, we can reduce the amount of iterations that are needed to converge in iterative methods such as conjugate gradient. We can use the preconditioner on GMRes also. We have tested that. Also, since the iterations that we do with our method are less expensive than the algebraic multigrid, we can achieve better performance as compared with the algebraic multigrid with a direct comparison between them two. And we showed also very good scalability as compared to this state-of-the-art problem. What we want to do now is to actually improve this preconditioner to be able to solve more complex problems, and also to build that only use information from the matrices that come from the discretization. So, well, thank you for your attention, and also thanks FAPESP, CNPq, and also Petrobras for the support, and CMI also for the support. Thank you very much.
Thank you very much, Fabricio. Thank you very much for this really nice talk. Great results there. And let us ask for the audience if you have for possible questions. Do you have any questions? Are there any questions? I don't know if you just open the audio, the microphone, or type here in the chat. So I have one. So, Fabricio, it was not clear. All these tests you tested with the 2-point flux approximation on that one. Okay.
Yeah. These are all solutions of the standard 2-point flux approximation, and with conjugate gradient, but it's preconditioned by our method.
So it's pretty good. It's like ready to use because it works in the most common and famous method that's applied in this kind of problem, right?
Yeah, it is. The drawback is that this is done for this pressure problem. So if we want to solve like a more complex problem, we have to change it a little bit. So this is why we are trying to achieve a true algebraic method to build that using only information from the matrix.
Okay. So for example, if you have a Javier-Tomás solver, it's not straightforward to apply this to.
Yeah, I mean, it has to be like it has to be a
Pressure constant.
pressure solving. Yeah, only pressure.
Right.
Yeah, it's
Okay.
not ready for a mixed discretization, for instance.
Okay. But for example, if you have some standard Galerkin, H1 Galerkin in pressure, that's pretty good for pressure, but it's not like a piecewise constant. You have a nodal linear interpolation. Is there a way to like communicate these two problems? The standard Galerkin for H1 approximation with some kind of use of this
Yeah, we can
precondition.
do that. Any pressure solver direct that we have like
Only.
that we
Okay.
have the solution of AX equal to B, right?
Mhm.
So we can use our preconditioner with that.
So it doesn't need to be like a piecewise constant pressure. You can have any pressure. You can use these ideas there.
Oh, I see. Yeah, we haven't tested that, right? But
Mm.
I think that we can do that with
Yeah, you need to adjust because even the number of degrees of freedom is not equal. So, but
I
it's
don't
pretty
know.
interesting. Yeah.
I don't know if we will achieve the same performance, right? Because
Uh-huh.
this performance here is because we are using more or less the same thing to build the precondition, right? The same. We know the discretization that has been done, right?
Mhm.
We are using the same to build the precondition. Yeah.
Perfect. So congratulations.
Okay.
Are there here from the audience? I probably there are not.
Michael.
Okay.
Uh,
Denise.
yes, yes, it's me.
Oh, Denise.
Hello, Fabricio. Yes.
Hello, Denise.
Uh, Congratulations for your presentation. It's a very good subject and interesting, and I know that you have been working on this subject for some time, no? So let me ask about your preconditioner. Can you come back for the slide where you defined the preconditioner, please?
This one?
Yes. One more
This one, right?
back. Yes. Yeah. This preconditioner was defined by your team, right?
Yeah. Yeah, it is.
And what was the idea behind using this part elements in this preconditioner part of your
Yeah,
is
yeah. I mean,
yeah yeah.
what we did
Yeah.
was
What was the idea kind of works for your I don't know if you that Michael already did. If you have this, if you have a formulation that has this algebraic system, you can, independent of the base you use, you can define the same preconditioner, no?
Yeah, I mean, let me put in this perspective here. When we want to use the preconditioner inside the conjugate gradient method, we have to apply the preconditioner like in this line here, right? So this means that we have to solve a problem, right? To obtain this z, right? With the right-hand side being the residual, right?
Yes.
And the matrix of this problem, actually, if we take out this line and solve this problem here with the multiscale method that we have directly, without assembling any matrix, then we will have our preconditioner, see? So these computations here are the realization of the algebraic version of our method, right? So we show that our method can be written in algebraic form in this coupled system that you see here, right?
Mhm.
And to arrive to that matrix, what we do is to isolate the pressure. So we try to write here the system in terms of pressure by eliminating all these other unknowns here, right?
Mhm.
So when we do that, we arrive at this ugly matrix that you see here,
Mhm.
very large matrix. But I mean, this is actually the matrix of our method, right? So this is equivalent. But we don't assemble the matrix like this because it's too cumbersome to do that because you have to invert the matrix and look
Yes, yes.
box and etc.
Okay. Okay. Thank you.
All right.
Good. I think we need to thank you again, Fabricio. It's really nice talk. Very interesting, and you have open questions there. So it's a research that we hope to hear a lot more about that in the near future. So I think we can stop recording. I